This is the second lecture. We're still reviewing basic general chemistry concepts. Today we will be looking at quantum numbers, and at the end of the lecture will be able to assign the 4 basic quantum numbers to any electron in any atom, whether it's a valence electron or one of the lower lying electrons in a d, s, or f orbital. And so just as a reminder, all of the matter is made up of atoms. Atoms have 3 subatomic particles: protons, neutrons, and electrons. The number of protons that are contained in an atom indicates what element it is, what reactivity you might expect. And so an atom that has 2 protons is always going to be helium, and then it can have a number of neutrons in the center. In this case we have 2. And you also understand that we have different isotopes, and we can have varying number of neutrons, but that doesn't have any effect on the element's chemical characteristic, but could have an impact on the nuclear reactivity, where if the neutron to proton ratio gets too high or too low, it can undergo radioactive decay. You can have a beta particle or an alpha particle, but that's really not chemistry. As I said, even if you have a radioactive isotope, the chemistry of carbon-14, for example, is still going to make 4 bonds to another carbon, whether it's carbon-14, 13, or 12. Also important is that most of the matter is inside of the nucleus, contained in neutrons and protons. They have roughly the same mass here, 1.6 times 10 to the negative 24 grams, so extremely tiny. And so these are clumped together in the center, and then we have electrons that are mobile. They go around in different orbits. This here just shows for simplicity a sphere, and for the helium atom you have 2 1s electrons. It happens to be true that we have an s orbital, so it is a sphere. But electrons have roughly 1,700 times less mass compared to neutrons and protons. So they basically just take up space and don't have negligible matter. And I like to, this is already a zoom, right? We've zoomed in on this atom. I like to zoom it up even more to the size of a baseball field here. So if we increased the radius or the size to the infield here, which is 90 feet by 90 feet, that's a rather large atom. If this was hydrogen, we would have a single proton, and it would be on the center here, and then the electron would be hovering around also in this s orbital, right? And so just to put this into contrast, how much smaller the nucleus is compared to the space that the electrons fill out, that would be the size of a fly in the center here versus the entire infield. This is where those electrons are hovering around. Of course, it's sometimes difficult to draw that this is spherical, right? This is not a 2-dimensional surface. This is it's a soccer ball, right? So it also comes at us, and so it really fills up a lot of space. So in order to study the electrons of these atoms, we look at quantum numbers, right? And so we can study the electrons because they can give off energy signatures. Let's say we have a cobalt atom. Cobalt has 27 electrons, and each of those electrons has to have a unique set of quantum numbers. And that's because 2 electrons cannot occupy the same space at the same time. And so this is why we use these quantum numbers. And so we know that we can study the electromagnetic spectrum. And so what happens is we have these different quantized energy levels here that are just shown as 1, 2, and 3. And these electrons occupy these energy levels, right? It makes sense that you have an electron that goes around. It's going to have a certain amount of energy. So let's say the first electron here in the 1s goes into this first orbital. And then we can put a second one in there. It also is in there, but it cannot be in the same space. So we conveniently say has spin up and spin down. I'm sure you've seen orbital diagrams in Gen Chem where we would write 1s and then hook up and hook down representing just that. That's Pauli exclusion principle. And so these would be on the first energy level, and when you add a third electron, there's no space here. We go to a higher energy level, so it's going to have to travel at a faster speed, and therefore that would be going to the second energy level. So all these energy levels exist, and so if we excite, we put some energy into an atom, we can get these electrons to jump up to a higher level. For example, here, this transition shown is an electron jumping up from the first to the third level. And sometimes all it takes is a little bit of sunlight, or you turn on a lamp, right? Because every time we see something, that's electromagnetic spectrum. That's an electromagnetic wave that our eyes detect from the transition of these electrons. But it's not the energy that is absorbed that we see. It is the energy when this electron comes back down, right? And so the electron from the third level coming back down to the second level, in the case of hydrogen, that's probably why they show it to the second one. That's one of the transitions that we can see. And so this energy is given off as the form of a wave. And so waves have two components, as you know. It has a wavelength and a frequency, and so the frequency can be used to calculate the energy of an electron or any particle that travels in the wave, and that's what mu is here. And so Planck was one of the major scientists who discovered that these electrons can have quantized energy levels, that they can either have energy level 1 or 2, right? So we can calculate the energy of an electron with Planck's constants times the frequency. That gives us the energy, and so then we have whole numbers 1, 2, and 3. Those can be the energies. They cannot be 1.5 or 1.7. So that was actually an interesting observation, that energies can have quantized, that electrons have quantized energy levels. And so one of the things that Planck studied were solids. So he would take different metals and he would heat them, and you would expect if you heat up any object, its thermal energy, of course, would increase linearly, right? So you can gradually increase the temperature of any object, and you would increase its thermal energy, and that would be a linear graph, right? Not the case for these electrons. So he also observed that so again, the color that we see of the cold object, that silver, is the energy that is given off by a number of electrons that are coming back down to a lower level. So it gives off this electromagnetic wave. And so then we can, if it's in the visible range, we can see it. So if you heat up, so this is now the energy of an electron. If we heat up the solid, and I'm going to make up these temperatures. I sure don't remember what they were. These can be easily Googled. If I have an iron block and I heat it, it's not going to change color. So that means that the energy of the electron doesn't change. And then at some point at 300 degrees Celsius, it will start glowing in red. So that's what we see here. And so that means the energy now jumps up and it glows in red. So you keep on heating that and it'll glow in red all the way to about 1200 degrees Celsius. And at that point, it's going to glow white. So it's going to jump up and then level out again. And so this is how one of the experiments that Planck used to deduct that, okay, so these energies either have energy 1 or energy 2. They're not in between. So that was that was a groundbreaking discovery back in the early 1900s. So what we're going to do is we're going to give each electron a unique set of 4 quantum numbers. And so this is the summary here. We have principal quantum number, the energy level, and that's reflected in the periodic table. The periods, first period, second period, third period represents the energy level. Of course, an element that has valence electrons on the third quantum level also has electrons in the first and the second. And then So that would be quantum number L, simply the energy level. And then we have the angular momentum quantum number, which is L. And that's just the shape. We already discussed the sphere, which is the s orbital, and or we have p orbitals. They are dumbbells, right? And so the magnetic quantum number m sub L is the direction. A sphere wouldn't have different directions. A sphere doesn't matter, but we also know that we just have one s orbital, right? But we have three different p orbitals in three different directions. So that would then be the direction, right? So if we have a px or a py or a pz, the shape would be described by L, and the direction would be then described by m sub L. So we can have, as you know, 6 electrons in that in a particular subset of L's, like in L, 2p, for example. And then finally, if we have 2 electrons in the same direction, in the same quantum level, we basically have m sub s, which is the orientation spin up and spin down. Okay, so let's go through each of these. You can determine how many electrons can be held by a particular quantum level by simply using a whole number and squaring it, right? So if you have 1 squared, you end up with 1. That means we can only have 2 electrons max, right? Because if you want to do the electrons, you just need to say n 2 times n squared. So for number 1, you can have 2 electrons, and we know that because the first period only has hydrogen and helium, and so that's 2 electrons, and you're done. And then you have to go to the next quantum level, and so if we take 2 and we square it, we get 4, which is also clearly reflected on the periodic table. We have 1s and 3 p's, which makes it 4. So the 3 p's, that makes it the 4, and so on, right? You go to quantum level 3, you also are inserting the d's. Of course, the d's are shifted. We'll look at that at the next lecture. And so in theory, you can have s, p, d, f, g, and so on. They are there. They're just more difficult to populate, right? You have to stick energy into an electron to get it to go to these higher levels. Right, so that's the first quantum number. You should be able to calculate or determine the maximum number of electrons held, for example, for the 4th quantum level by simply doing this n squared times 2 calculation. So the angular momentum, or the shape, is L, and it starts at 0. So if you have a quantum number, the principal quantum number n, if that is equal to 1, then n minus 1 tells you the highest angular momentum possible. In this case, for quantum level 1, we know it's an s orbital, and so s orbitals are given L equal to 0, and so 1, 2, 3, 4, it just simply goes up as then P, D, F, and then G. As I said, we don't have those observed in the ground state, but it's still a theoretical energy level that is available. So that's pretty simple. And then you can also calculate the total number of suborbitals within the angular momentum by 2L plus 1, right? So if and I have these calculated here, and you know this, that the s orbital has only one direction, and so this would be the direction now. The next quantum level, m sub L, can be calculated by that. Right, so this would be m sub L already going ahead. And then we have, of course, 3 p orbitals, 5 d orbitals, and 7 f orbitals here. So then what you do is let's look at some shapes here, right? So here we have the p orbitals, the x, y, and the z, and so you already know this, right? This electrons, and this is a nice little cross section here above. It also shows the electron density distribution a little bit. So most of the density is going to be located here, and then you have some further away. We'll look at radial density functions in a second. So p's, the s orbital, we know is a sphere, and so I have this here in blank. We're going to look at the 5d orbitals. At some point you will probably be tested on giving the designation, just like you should be able to do px, py, pz. And so the d orbitals are interesting, but and I'll bring it up in a second, kind of clean. But if you write an x, y, and z coordinate system, you will have one of the orbitals that is along the x and the y axis. All right. So let's make this the z. So this is the x and the y, and so this would be called the dx squared minus y squared. The reason I'm showing you this is so that you can deduct this logically yourself without having to memorize it. So then if we occupy two of these x's, we're also going to probably have the z-axis occupied. All right? So this is the dz squared orbital, except all of the d orbitals have two regions, and so there is no room on an axis, so the second region here is in form of a donut. Okay, so that second region is right there close to the nucleus. So that's the dz squared, and then we have three left, and they all are in between the x's. So if this is the x and the y, you would have, and this is a little harder to draw, right? So this would be the dxy, and then we have a dxz, and then we have a dzy. And so the best way to draw that is just to relabel probably the x's. So if you can just draw it like this, and just say this is the x and the z, and then that would be the y. You leave the one that doesn't have any lobes out. You can easily come up with those four shapes yourself. Here they are cleanly written out, right? So here's that dz squared I was talking about. It's along the z-axis. The x squared minus y squared is also along the x-axis. And then the other ones are in between. Of course, this is much nicer than what I drew. And then finally we have the f orbitals, which have several different regions. And so this is just so you can see there's 7 of them, as we know, and they fill out interesting regions. And let's back up a little bit and go back to a 1s electron here in the hydrogen atom. So we're looking at the radial density function for that electron. And so on the x-axis we have the distance from the nucleus here all the way to 150 picometers, and phi here, of course, phi is from Schrödinger's equation, is the wave function. Phi describes the behavior of an electron within an atom, which we all know is very difficult to do, and that comes back down also to Heisenberg's principle, Heisenberg's uncertainty principle, which states that you can either locate the position or the velocity of an electron, a particle in motion, but not both. And the difficulty to determine that, of course, is because electrons or particles like this have dual personality, so to speak. They behave like a particle, but also like a wave. So if they travel like a wave, but they have mass, it is difficult to determine its position and its velocity. Right? So if you think about it, if you can determine its position here and then here, you would possibly predict, if it was a larger mass object, that it would travel in this direction, but you really can't. And so on top of that, we have this we're going to go around in a sphere somehow, fill out some sort of orbital, so it makes it even more difficult. But Heisenberg's uncertainty principle is essentially the change in position here times the change in velocity is equal to Planck's constant over 4 pi times the mass of the particle. So again, you can either determine the position or the mass. Of course, we know the mass of an electron, either the position or the velocity, but not both. Maybe it makes more sense if I draw a sphere, and so if you have the position here, it can go. We don't know if it's going to go here or here, and even if we have two positions, we cannot assume that we have a linear trajectory, because of that dual wave-particle duality is what they call that. So it's more useful to look at a probability function where we can now look at regions of electron density from the nucleus. This again is for the electron and hydrogen. And so now we have, of course, we have no electron density at the nucleus, and then the majority of your electron density is at this maximum. This happens to be the Bohr radius. And in the case of hydrogen, it is 0.52 angstroms or 52 picometers, and that happens to also be what we use for atomic radii. So that's much more useful to know that than looking at the radial distribution or density function, where we square the wave function to get a probability. So we just looked at the 1s orbital, also looking at the two higher ones, the 2s and the 2 and the 3s. It makes sense that we would have our electron density shifted further away from the nucleus, right? It has to travel faster to be further away from the nucleus, and so we the maximum here is further away and further away for the 3s and the 2s compared to the 1s. And so what is interesting here is that we still have a little bit of electron density distributed closer to the nucleus, and then there are these areas where we touch the x-axis. That means there is zero possibility of finding electron, and so those are called nodes. And the cross section here, those contour maps, really show very nicely where those regions are completely in white. And there's not much to be said here except note the nodes, and we can calculate the number of additional nodes. There's always one at the nucleus, and so by using this formula here, n minus L minus S, n is the energy level, L is the shape, and then 1 is just an integer. So for 1s we would have 1 minus 0 minus 1, which equals to 0. So there are 0 additional nodes. For our 2p, we would have principal n equals to 2, p is equal to 1, so it's minus 1 minus 1 is also equal to 0. We have 0 nodes. For the 2s orbital, we would have 2 minus 0 minus 1, so now we have 1 node, and then here we have 3 minus 0 minus 1, so that would be 2 nodes. Here are just some nice pictures. We already looked at them, but they are blown up. The white region here, you can clearly see that we don't have any electron density there, and so we have more. Most of the electron density is located here, and that goes right back to that maxima of that 2s for the distribution function. Here's the same picture, except now we have a three-dimensional representation, and a wedge is cut out. If it helps you see those regions, I always like to look at pictures. It really clarifies things. So, of course, we're looking at a hydrogen atom with 1 electron, so these are pretty simple. We are more interested in looking at molecules, right? So here we're looking at an ethanol molecule, and so we have the space filling model here, which tells us a lot. And we also know this is polar, right? We have a carbon oxygen and an oxygen hydrogen bond, so we have got a polar bond here, and so a negative and a positive region, so we know it's polar. It's going to mix with water. We also know that these stick to each other through hydrogen bonding electrostatically here. That's an intermolecular force that's holding these molecules together, makes it a liquid. And so what you see here on the right is called the electrostatic potential map. It's a calculation based on data that we have for the ethanol molecules. And so in red here, we can really see where that negative charge is, right? So it's one thing to just write a delta minus, but it's much more interesting to see where the blue and the red regions are here, or the green, and so we have the negative in red, and then the positive in blue. So those pictures are much more useful. Now let's get back to our quantum numbers. We've done n, which is just the principal energy number. We've done L, which is the angular momentum or the shape, and now we're going to do the direction, which is m sub L. And so we already looked at the number can be determined for how many different directions there are for one principal number L. So for example, if we have S, we can only have one L, and if we have P, we can have three L's. And so if L is equal to 1, we know it's in p orbital. We can have three different orientations, px, py, and pz, and the way we would write it is like this: m sub L equals -1, 0, and 1. So for L equal to 0, it would just then simply be 0. So that would be one direction. So this could be the px, the py, or the pz. We don't know. It doesn't matter. It's irrelevant as long as each electron has its own set of quantum numbers. And then finally, if you occupy the same suborbital, then two electrons can be held in that, and they have to have different spin. We just simply say +1/2 or -1/2. This is a summary of all of the possible quantum numbers up to the fourth quantum level here. That includes the F electrons for m sub L. M sub S is not shown at all, but I'm more likely to, you should be able to reproduce that if I ask you for all of the possible quantum numbers for ground state electrons in potassium, for example. You should realize that potassium has the highest quantum level is the 4, and so you should be able to come up with, of course it doesn't have the D's, so it would be here. So you would have to produce all of those there. But I'm more likely to ask for a specific electron. Maybe I'll ask you for a valence electron of rhodium, or I'll just more specifically come out and say I would like to have all 4 quantum numbers for a 3D electron. And then all you have to do is give me N, give me L, give me M sub L, and give me M sub S. And if you don't remember anything, you can just write +1/2 and -1/2, and that's always going to be the case. Sometimes they even leave that out. So, alright, so N is the energy level, and the large number in front always refers to that energy level. So N equal to 3 here. And for L, so be careful, it's not necessarily N minus 1. That is just the highest possible value for a subatomic orbital of the third quantum level, but here it's dictated by D. Right? Remember that S is 0, 1 is P, and 2 is D. So D is 2 here, or L is equal to 2, and then M sub L, we gotta have 5 of them because we know D orbitals are 5. So we go -2, -1, 0, +1, and +2. Those are our 5. So that's easy. Let's do the 4s. N is equal to 4. L is equal to 0 because S is 0, P is 1, D is 2, right? And then M sub L is just -L in integers, and so since it's 0, it's just 0. And then, as I said, M sub S is just +1/2 or -1/2. All right, let's practice a couple more. The 4 quantum numbers for a 4f electron. N is equal to 4. L is equal to 3. And so we expect to have 7 M sub L versions. So we go -3, -2, -1, 0, +1, +2, and +3. Those are the 7 suborbitals, and M sub S is just +1/2 and -1/2. Okay, how many nodes? All right, so for 4D, we have N is equal to 4, L is equal to 2, and then M sub L is just -2 -1, 0, plus 1 and then plus 2, and again f sub s is equal to plus 1/2 or minus 1/2. So this concludes the introductory lecture. We're going to move on to the periodic table for the next set of slides, and you may want to think about this question.